So this is our example, Moore's Law. We've already talked about it, but I'm just starting to record right now. So this is linear. We have ln right here. So you only have ln of the y variable. So to do one like this, Minitab output from a linear regression analysis of the transformed data is shown below. Give the equation of the least squares regression line. So we need to use this, and it's really similar to what we were doing before. The only difference is you're going to have ln because we transformed the data. So it will look like this. Ln of y hat is your y-intercept. Y-intercept is this number, 7.0647, plus the slope is this number, 0.36583x. So really similar to what we did before, but if Minitab gives you transformed data, then you're going to have ln y. You might have ln over here, or you might have one of each.
I have a question.
Yeah.
Are we ever going to be given like all the data and have to go through and like give the natural log to every y?
We're going to do that on Monday. But it's a lot more common to be given the graph. In the book, it's more common to be given the graph. In real life, you never, you collect the data and you graph it and see, oh, this is not linear, so I need to do a log.
In physics, we would square it. We'd square the
Yeah,
data.
so that's a power model.
So is that kind of the same thing?
Yeah, instead of squaring it, you could have done a log of x and a log of y, and that would give you a linear path, a linear model. Use this model to predict the number of transistors in 2020. So that's our x. So it's also important to notice this year since 1970. So if you're going to 2020, you're not plugging in 2020 into your formula. You're plugging in what?
2020 minus
2020.
yeah.
2020 minus 1970. The year since 1970. How many years have been since 1970? That would be 50 years. 50 years is what you're plugging in. So you would plug into this formula. You'd have ln y hat equals 7.0647 times 0.36583. And this is 2020 minus 1970. So it's 50. And that's, bless you. So we can get the right side of the equation, 7.0647 plus 0.36583 times, order of operations is okay here, times that. You get 25, 35, 62. 25, 35, 62. And you have ln of y hat. And basically when you undo the ln, you're undoing the natural log that you had taken. So it will basically convert it to an answer. If you had written an exponential function, it's converting it back to the exponential function you would have had. So it's just a lot easier to do this work rather than to try to write the exponential function.
So if we raise both to the e, or if you, then it would be the actual number of transistors.
Yeah, but like you'd need the formula of them. So yeah, if you raise this to the e to the 25.35.
That would be the number of transistors predicted in 2020.
In 2020, yeah, that's our predicted. So you would have this answer. The E button is second ln. They're inverses, so they're on the same button, which is really nice. 25.3562. So you get 1.028 times 10 to the 11th transistors predicted.
Why did 10 to the 11th?
Because it's a very large number. What it was, let's look at the data. What it was in 2010 was 2.3 times 10 to the 9. So 10 to the 11th is multiplied by 100. So after 10 years, it's gotten 100 times bigger.
Wait, you did
is the prediction.
You didn't e to the 25.315.
Uh-huh. 25.3562?
You second ln, right?
Yeah.
Yeah, I got 9.866.
On the next example, on July 31st, 2005, Jacob, thank you. A team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 9.5 billion miles from the sun. Could this new astronomical body called Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. Here are the data on the distance from the sun in astronomical units, AU, and period of revolution for those planets. So a period of revolution is how long it takes to orbit the sun. So Mercury doesn't take very long. It's all based on Earth, so 1 Earth year to orbit the sun. Distance from the sun based on Earth, is 1. So these are close, these are far away. Pluto's there, Eris isn't on there, but you have the number right there. So here's the data, which is a slightly curved pattern, like that. Describe the relationship between distance from the sun and period of revolution. So it's positive and it's slightly curved. Positive relationship, because positive in the sense that as distance increases, then the period increases. Which should make sense. The farther you are from the sun, it takes longer to orbit the sun. So it's positive and it's curved. On the next one, you're given a scatter plot. Based on the scatter plots below, explain why a power model would provide more appropriate description than an exponential model. So notice, again, it's really important to notice your units. This is distance, no ln on that one. But this one is the natural log of the period to orbit the sun. Compared to this one is ln and ln. So if you have ln of both versus ln of 1, this ln, anytime you have 1 natural log, this is the exponential model. It relates to the exponential model. And this is the power model. So once you know that piece of information, you could say, well, a power model would be much better, because look at the graph. This is, if I can actually hit the points, this is incredibly linear with this power model logging both variables. Compared to an exponential model, you don't get a linear pattern if you only ln the period to orbit the sun. So a power model would be much better because you produce a linear scatter plot. We need to have output from a linear regression analysis on the transformed data is below. So it used to be distance to period, but then we ln'd both variables, just like we did right in this one. ln distance, ln period. Give the equation of the least squares regression line. So in this case, it's going to look something like this. Example right here. So you're going to have ln y equals the y-intercept plus the slope, ln x. So you're going to have 2 ln's, and we're going to have to solve that. There we go. So we have ln of y. The previous one we didn't define our parameters, so we'll just do ln of y, ln of the period. So we don't have to define the parameter. That's actually, the whole thing has a hat. Hat equals the y-intercept, this number, 0.002544, plus the slope, 1.49986, ln of the distance.
There's 3 zeros.
Yeah, it's 0.00.
Sorry. So define any variables we use. This is period, this distance. What, problem?
The decimal's supposed to be 1 to the left.
Oh.
And the y-intercept.
Thank you. So that's better. Use your model to predict the period of revolution for Eris, which is 102.15 astronomical units from the sun. So you're given which variable, the period or the distance? Distance. So you have the predicted period period hat equals 0.302544 plus 1.49986 ln of 102.15. So you could type everything in on the right into your calculator and then get rid of the ln on the left side. So you'd have 0.0002544 plus 1.49986 102.15. So you get this number, 153.21. ln period. So the predicted period would be, algebraically, how do you solve that?
Wait, how do we get rid of the ln on the other side?
Oh, did I not type it in the calculator?
We'd have to raise that 153 to the E whatever.
Yeah, sorry, I have to go back. Fatal flaw. Right here, I forgot the ln. So thank you, Kelsey. And I didn't type it right. Oh. (1032 Earth years). Last question is, residual plot is down here, given for the linear regression in part B. So this one. Do you expect your prediction in part C? Our prediction was 1032. Do you expect it to be too high, too low, or just right? So 1032 is our prediction, Earth years. So remember, a residual is the observed minus expected. And a residual is distance away from your prediction, your actual line. So, if your line is here, not this residual plot, but if your scatter plot, line of best fit is here, and you have a point here, and you predict, you make your prediction here, this would be lower than expected. If this is the reality, then your line gave something lower than expected. And this would be a positive residual. So, how do we use this residual plot to figure out if it's too high, too low, or just right? So we were given 102 astronomical units. ln of 102 is what? So we're looking at over here somewhere at 4.62. So notice these points are all above the line. And it looks like with this pattern that our point's probably going to be up here somewhere too. So all those points around 4, if the line is here and the points are there, then our estimate would under-predict the actual Earth years.
How did we determine that?
Because here are the planets.
Okay.
Here's the line. The line that we're using to predict. Here's the reality. Our prediction would be below the reality.
Well, our prediction is 4.62.
Well, 4 is the x, and these are like basically the predictions, so to say, the residuals.
Okay.
So all these planets are above the line. So if the planets are above our prediction, then we under-predicted.
And where's our prediction? How did we calculate that?
For 4.6, it's out here. So given these points, our prediction is most likely similar to these points, because points, the points are getting higher if you see this pattern.
Okay.
So our point's probably up here somewhere, so the line, our prediction is on the line,
Oh.
and the reality is where the star is. So we would underpredict with the line. Sorry? Oh, the 102. The 102 is given right here. So, like, Earth, I guess, would be right here. Because the planets are generally farther away. So I would guess the third one is Earth.